And welcome to the desk of Lady Ada.
Hey everybody, it's me. It's Lady Ada. But with me is yet another person. How is that possible? Through the magic of trains, we have Amanda, the Wozniak.
It's a pleasure to be here tonight.
Thank you for coming all the way from Boston, Cambridge, Somerville area to fabulous New York City, which is where we are now. We have fed and watered and bathed the Amanda, so she's ready to just go full on engineering hog. Whatever that idiom may be is going to happen. We're
here with jokes, puns, metaphors. We've been hanging out for...
We're on air.
We're on air. We've been hanging out for a couple of days.
It's already gotten a little wacky.
Yeah.
Phil has already been like, I'm leaving because you guys are just talking about skin effect.
Yes.
Too much engineering.
There was like a full half-hour discussion. Maybe we'll talk about skin if people ask.
Yeah, cabling.
But what I got on Friday that I thought you would love, because if there's one way to a woman's heart, it's wafers, is I got these wafers. Ooh, aren't these nice? I got a pack of 6. And I got these because we're actually going to be doing a video. This is not out yet, don't ask, for the next Circuit Playground. For I is for integrated circuit. And so we thought maybe we'd take some photos.
Right, with Hans the 555.
Yes. Well, you just gave away secret. That's okay. Shh. It's not out yet. Well, maybe the people who watch, maybe they get insider knowledge.
Bring your plush.
Bring your plushies. Okay, so I got a pack of 6 of these, and people might be asking, why is this woman here qualified to talk about silicon wafers?
Well, so actually my initial career before I switched into medical was semiconductor engineering. I worked...
Is that so?
It is so.
Wow.
Oh, wow. So it's so nice of you to ask. So I worked at Intel Corporation, IBM, just really small companies.
Oh, these are like little teeny, like they're like big little chip fab. Like,
yeah, they're just privately held chip fab.
And then individual. They make one chip.
Yeah, and then I worked at a very small MIT startup called Analog Devices.
Also.
Maybe you've heard of them.
No, I don't know.
So I worked in semiconductors all through school. And then also that was my first position outside of school.
Yeah.
And I was in semiconductors when I realized I wanted to make the transition to system level medical devices.
Okay.
Because semiconductors are fun, but power, there's a lot of other design challenges that I really like.
So you cut your teeth on silicon design?
Yes. Well, not yet.
Not literally, because these are toxic.
Yes, they are quite toxic.
This is something Waz told me. She's like, oh, by the way, like the wafers that you get, even like I got these from an eBay seller, they're actually don't lick them, basically.
Right, even if they're...
Don't serve food on them.
Right, even if they're passivated, that doesn't mean there is not a lot of contamination and also byproduct of the etching and processing steps that are really no good for organic life forms.
Okay, so there's somebody out there who is just like, I don't believe Waz actually did any silicon design. Where's your GitHubs? And it's like, well, whatever. It's just this thing that guys say when they're like, this lady that proved to me. So was there any chip that you worked on that you can be like, yeah, this is a chip that I worked on?
Yeah, I actually worked on the AD819X series of HDMI multiplexers.
Oh, you mean this buffer 2-to-1 TMDS switch for HDMI DVI high-speed signals?
Yeah.
Wow. Also, a great coincidence that I had that data sheet pulled up. I was just designing a 2-to-1 high-speed signal switch. What's funny is we actually are using a 2-to-1 signal switch right now for this video setup.
Yeah, and I was actually really impressed by all of the HDMI cables, and they've really improved, it seems, the signal integrity of all of the parts around the HDMI application lately.
Yeah, and about what year did you work on this?
I worked on the HDMI parts from 2005, 2006, 2007, and 2008.
Okay, wow, that's a lot.
So yeah, we actually released a huge number of parts. I was not a designer though, just to correct that. I was an applications engineer.
So you worked on these chips?
Right, and I worked primarily on the chips were already in the packages doing, I wrote the data sheets. I wrote this data sheet.
Wow, what's lovely.
And
this is a great little drawing here.
Oh, that was done by corporate. But I did, no, like I would actually do, I did that
You did the
graphic as
text.
well. So
Okay.
I laid everything out typically in Illustrator,
Yeah.
which is why I used to use Illustrator for designing the ice tube clock enclosure. That's how I got so good at it. But I wrote the technical data sheet. I worked with product and test engineers to generate the data. We put a lot of work into the typical performance curves. I worked a lot with the test engineers for, so that everyone splits the process out. So you've got the designer, and then we have the transfer to manufacturing, which has the product and manufacturing liaison. And she was amazing. She
Yeah.
ran a very tight ship. She was the gatekeeper between our design and actually getting our chip on a reticle to get real die back, to get wafers back.
What does a reticle?
A reticle is basically a grid of available space for doing lithography for semiconductor printing.
Okay.
So the way
It's like a stencil.
it's a stencil,
But it's a very small stencil.
well, it's a multi-X stencil. So you'll have a reticle is a step and repeat stencil for your chip, and in fact, actually, so we have. Well, this is a less good
This one's
example.
not-
I think this
Like this
one.
one?
Yeah, let's get this one is clearly.
Here, I'll turn off this light so it's on.
Do you have that one?
This one?
This one.
This one.
Yeah, the crazy one.
Okay, well so we got these wafers. We got 6 wafers. It was like a 6-pack.
It's one of every flavor.
This basically, except don't lick them.
No, no
and
licking.
so this one's really lovely. And people are probably like, wow, I wish I could see this under some sort of like microscope. And we have an HDMI microscope.
Yep.
So maybe let's check
Topically
this out,
appropriate.
and we can talk about
What's going on here?
reticles.
So if you look at this chip, I'm actually going to take it over to the higher level cam.
Okay,
first.
so let's go to big overhead.
Big overhead.
Yeah.
So if you look at this wafer from above, there's a whole lot of. It looks like there's a large scale grid, right?
Yeah, so it's like you can see this, like this is one group, and then this is
Right,
there's
another
like-
group.
There's groups, and you can see like especially when they sparkle, they can see how like not all of them do. It's
Yeah.
like a grid of 9. It looks like
Well,
a subgrid of 9.
it's like a subgrid, yeah. So you've got a step and repeat unit here, and the reticle is the mask for
Okay.
actually doing that.
You
Step
know,
and
we
repeat.
can actually move this up if you wanted to like.
Oh, actually see the whole thing.
Yeah, so you can go like this, and then you can like zoom like that.
Yeah, so that's actually this reticle is quite large.
Okay.
But you can see that there are each one of these smaller individual
Oh, wait, hold on.
squares.
Can we go to the
Go
micro?
to the.
Sorry. So much going on.
I can draw all sorts of little.
There's nice
pictures.
tweezers, right?
These
Just
are
got-
really nice tweezers.
These are like some
They're
tweezers.
so sharp.
Yeah, if you want, you can keep this.
So if this is a horrible circle with the flat part, which you actually need for doing the dicing, the reticle is this step and repeat square unit across the wafer.
And is there a
surface.
set number of reticles, or is it like it depends on the process?
It depends on the process. It depends on the wafer size. It depends on how the fab is set up. It depends on all the equipment.
Okay.
So the answer is it depends.
Okay. Okay.
So
So this is so you can see what you see here.
So this is a multi-chip reticle, and you can see that each chip has its own dedicated area that's
Wait, so
equivalent.
how big are those? Are like about 2 millimeters?
They look like to be about
3
2.5 millimeters on a side.
Okay.
And each one is a different part. Now, this almost looks like placeholder. There's nothing here except
Yeah.
pads. So these little pads here around the edges are where lead wires are bonded. So those are bonding pads.
Yeah.
So-
yeah, the little dots,
little-
they
yeah.
look like I want to say like nonpareils. You know what I mean?
Yeah.
Like little
Nubbins.
nubbins.
Little-
and then
little
this
nubbins.
one, what's going on? Why is it like kind of a beautiful triangular shape?
That I don't know. So it's actually, it's possible. So the structures you can make on an integrated circuit
Yeah.
are you can make resistors,
Yeah.
capacitors, inductors.
MOSCAP, because you all call MOSFET MOSCAP.
Yeah, because it's a capacitor made with the MOSFET process.
Yeah, I know, that's funny.
They're different. You can, and obviously you can make transistors.
Really?
Tell me more. So
Okay, so what's that part? Because that looks like the orange to go to the right one and then up. Yeah, what are those two? Because those look like they're
so
cut in half, but they
so by not being a designer, it's actually hard for me to. So I never went through the process of not only doing the circuit simulation. I used to do circuit simulation in SPICE, which is the first
zoom in.
step in.
Yeah.
The first step in making a semiconductor is you simulate your circuit in SPICE. You actually instantiate every gate that you want to go onto the device, and then you do RTL. You go through a processing step where you instantiate each device in the layout block, and then it's a lot of pushing polygons to make an analog to digital converter, to put in resistors.
I mean, like, I don't know squat, but that triangular one?
These look like shorts.
Well, but you know what else it kind of looks like? Like, can you point it? Because I can't get in there. Yeah, you have to. So that triangular one, see how it's like you see the traces and then they go to a little bit of circuit and they go, it looks like it could be some sort of muxer or something.
Or a delay line. So
yeah, because you see the traces come in and then they connect to a little piece of circuitry and then so it could be gates. I mean, like...
Possibly. So normally if you had a switch matrix, it would look like a woven fabric.
You'd
see a lot of things going in and you'd see a lot of things going out, and then there'd be a point switch where you actually connect the routing paths. This one's interesting because you've got very fat, this one... You've got very fat metal coming around and going to something. So...
Like that one, the one you're pointing at now, it looks like, I mean, again, I also have not... I did a little bit of VLSI layout, but like, it was, it was like, you make a single... Like we made an op amp.
Yeah.
Right, I mean, it's very simple. I mean, maybe like some sort of...
Like 20 transistors.
Yeah, basically. Like, hi, I made an LM101. This is maybe like some sort of buffer or something? I mean, like, you definitely see like there's a trace going around, but there's inputs and outputs.
Yes.
Looks like.
Yeah.
Although they sort of seem to sync around.
And the problem is, it's really hard to see at this scale.
So I need to get a much stronger microscope. And then this, what's funny about this one that has like was cut in half? It looks like a photocell. I mean, I know it's not, but it looks like one.
Yeah, it also looks like it has an isolation trench across the middle.
Yeah.
So...
okay, and then what's going on with this sub-reticle?
No, so those are step and repeats of blocks inside the IC, right? So
but so there's sub-ICs?
Yeah, so what you do is when you lay out, say you have a really good A to D converter, or you have a really good memory interface, you don't want to custom design it each time. Because particularly for high performance semiconductors, your parasitics matter.
Oh, so for example, let's say you're making a sensor,
right?
And it's like a current sensor or something. You already have, and it's an I2C current sensor. So you already have the little I2C slave controller and analog digital converter, which is basically like 90% of sensors are the sensor itself, which is like MEMS or something, and then you have the A to C block.
Yep.
And then you've got the I2C.
You have the comms interface.
Comms interface.
Yeah.
So that would actually, you think that you would actually pluck those down, and then you would just draw a little metal.
Yeah,
traces?
exactly.
Really?
Yeah, yes, that is exactly what you do. Because if you have different device structures, like for stages of a filter, you want to optimize that layout for performance, and an analog performance is a very big thing. Like analog devices makes high performance analog parts. And so you optimize your layouts for all of the different parasitics and process variables that go in. So believe it or not, when you make this wafer, you can't control things like sheet resistance to be identical every time. You have to, it's like designing with 10% resistors to get a really, really high performance part. So
you have constant feedback loops and like adjustable sections that you can... It's
more that you want to optimize your design so that as your process parameters vary at the fab, it doesn't push your component out of specification. And so that means that if you have a really solid layout, you in fact do step and repeat it wherever you possibly can. It also helps you increase IC density, right? Because every square millimeter of silicon is money. But you have to worry about throughput.
Yeah, I mean, on one hand, you get the knowledge of like, okay, this section is going to work, but you do lose. I mean, it's not as efficient as routing it all together.
Yeah, but you would only gain like a 5% efficiency. It's a really small gain given the amount of work it takes and the amount of risk and uncertainty.
Okay, I'm already bored with this one. So let's go to the next one.
All right.
I mean, no, you're not boring. I'm saying like we've
looked at this one.
We've totally looked at this wafer, and ladies want to look at another wafer.
So do you want to see how the wafers are actually? Well, this one's actually really cool.
How about we show it on the overhead first, so people kind of get a sense of how big it is. So this is a really big chip. So
this really is.
So this one, let's compare. So this one It's a little bit tough. You have to kind of hold it at an angle because it's not mirrored.
Yeah, but each one is like 2 millimeters on a side, 3
Yes,
millimeters
these are
on
like,
a side.
you can almost see the repeating pattern, and each one of those was one of those chips that we saw. So it's like the real chip size is like, it looks like about a centimeter by a centimeter.
That's the reticle size, yeah.
So this one actually uses that full centimeter by centimeter.
It does.
So this is a big chip, and then
This really is.
this is probably a processor.
Yes, it's quite large. So generally, there are a couple of things I do know how to identify in a semiconductor just by looking at the wafer, and grids like this are almost always memory.
Yeah, because you have to put down a huge chunk of like flash and RAM. Can you tell the difference between flash, memory, RAM, memory, and EEPROM, or is it like?
I can't tell the difference. You probably could if you had large enough plots, or if you knew what the process technology was.
Okay.
But anything that's large like this is an addressable memory, and it's really dense.
It's very not only is it dense, but it has a grayish look because it's repetitive.
Yes, it's highly uniform.
Yeah. Okay.
And then down here, there's what I would you can tell by how it's repeating that the same shape is on the same side. So this isn't like a die mirrored. This whole thing is the die, or let's find a better one. Like this whole structure of these two memory banks, and then all of this. Yeah, this reddish thing is the key to let you know that that's one whole IC.
Look this into the microscope.
Yeah.
Okay. Let's get this going here. Let's get this party started.
Okay.
Okay.
So this is your memory.
Let me rotate this so it's like beautiful. Wow, beautiful.
This
so it's
really
exactly
exciting.
this. As you can see, it's right on the edges.
Yeah, and you can see that inside these are unit blocks.
Really?
Yeah.
So that's
because if you have one I/O, right? Like if you have a current mirror, if you have
this is totally not how I thought chips were designed.
Try to focus more.
Oh, it's not focused?
No, it is. I think you can get a little bit better now. Okay.
There you go.
Now back out a little bit. Just a little bit. A little bit.
so close, so close.
Actually, I'm gonna look at the other one.
There you go.
Oh yeah, I see.
Yeah.
Okay,
That's
okay.
nice.
Yes, so you wouldn't
It's
think
tough
you were,
if we let go, it's gonna be a little out of focus.
Yeah.
So sorry, but it's like it's very
Sorry, guys.
That's nice.
the layer of what we're looking at is extremely thin.
Yes,
How
it
thin is the layer of what we're looking at?
So I don't know the thickness of the wafer, but
But like the diffusion, it's like
depends
nanometers?
on. So the gate size, old school, the first semiconductors, old school transistor feature sizes. It's a 10 micron process, i.e. you can make a line width or a feature the width of human hair or 10x smaller than a human hair, depending on how thick your hair is. But then that goes down, to like 90 nanometers was really pushing it. When I worked in semiconductors, 65 nanometers was like oh my god, like we're working in 65 nanometers. It's the hot new process. No one knows all the process properties.
I totally lost all these numbers. So what were you using when you did this? What were the chips that you were working on?
And I don't actually recall, but Analog did a lot of 1.5 micron. Was established in the 80s.
Sorry, so micron, so 1500 nanometers.
Correct.
Sorry, units. Hi.
Units, yeah, orders of magnitude.
No, because like wait, 1.5 to 65. So we were at like micron level, and now we're getting to like tenth of a micron level.
Right now, 10 nanometer is the highest density process.
Which is actually you actually start to have like effects of light waves.
We actually had that actually happened at 90 nanometer.
Like the size of the wave itself is.
Right. So I had a friend at IBM where her job was actually to run pre-processing on mask design, because IBM was running at a process node where the fundamental wavelength of the light was on the order of the feature size.
Yeah.
And so
you actually had to space things out so that you didn't get reflections and signal between these microblocks?
Well, actually, it was even weirder. If you think about light shining through a stencil of any kind, and you kind of see how the edges get blurry and some things warp and some things look bent based on the angle of the light, she was running simulations to do the reverse of that. So instead of her masks having straight lines to make a straight line, if the line density was a certain way, it would bend. Yeah, so
it would have a skew.
Correct.
So that when the light bent around the stencil itself, because also now the stencil thickness.
Correct.
Is
It's part of a waveguide. Yeah.
Okay.
Yeah.
Ooh.
And
Yeah.
yes, so it's where
Electromagnetics.
well, it's so where your stencil is a waveguide, and so
Yeah.
the stencil looks funky so that it can actually make straight lines.
I wonder if the thickness of the stencil, the way they cut it, like, it, you know, I'm sure they have to polish it in certain ways to make it.
Yeah.
And then they have to take account for the polishing, because the polishing is going to also affect it.
Well, so mask sets are expensive. So the cheapest mask set we had.
You can't go to Canal Street and just pick one up?
No, so the cheapest mask set I remember working with was like 50 grand.
Which is actually not that much.
bad.
It's not that bad. Don't get me wrong, it's a lot of money, but it's like, we're not talking millions here.
No, well,
Like a small company could make a small chip.
I mean, it depends, and it depends. Yeah, they absolutely could, particularly if they're working in an established process. If they're working at an established process node where the fab engineers are like, yeah, we can crank these out all day. It's not finicky. We have high yield, et cetera. Where the masks are cheap enough to make, like 50K is not that bad. The real cost of semiconductor engineering is the time it takes to get stencils made, or to get your mask set made, and to actually process wafers through the entire fab line, from all of the different wafer processing steps, doping, ion implantation, you know, I'm putting all the layers of metalization on. And I can walk through this in a second.
Okay, we're going to. Okay, but
go do this.
let's look at this chip again. Sorry,
Yeah.
so we're here. So the thing that I learned today, what did I learn today? First off, well, I've learned so much. I've learned about friendship from you, but I've also learned, that, because I just was like, I didn't understand what these multiple bricks, because you can also see there's patterns. Like there's 4 of this thing, and then there's 4 of this other thing. I don't know what these things are, but I was like, oh, this, to me, when I looked at this, I was like, oh, this looks like a test. Do you know what I mean? It looks like, oh, this is like the mask test. But this is actually our processors made. So like, maybe those are bus matrices. I mean, they have kind of a gridded look. Maybe they're multiplexers or something.
Right.
And they actually will drop down 4 of those. And now, hey, great, now we got like 4 multiplexers.
Yeah, and then you just connect them in metal.
That's so insane. That's completely not what I would expect.
But it's super smart when you think about it.
Because PCB design does not really do this. Like when you do a PCB, because it's not nearly as complicated or as expensive, like you'll reroute, like no matter what the eval board says, I'll reroute. Like you put one down 2 or 3 more parts, you route the whole fucking thing over.
Yeah.
Like one resistor gets added, I'm gonna like rip up the whole thing, move it, and then reroute because it doesn't cost much.
Well, so you can actually do that in semiconductors. So let me walk you through what the wafer really looks like.
Okay.
So let's go to the big top down.
Yeah. Okay, well, this is going to school us.
Yeah.
I learned about friendship and semiconductor physics.
So if we look at a cross-section of a wafer, they go for semiconductor fab.
This is like if I was looking at it like this way.
Sideways.
Yeah.
So you have silicon.
Yes.
And then actually what happens is naturally if you put silicon in an environment with, you have to move heaven and earth to make a perfect silicon crystal. And a silicon crystal is where the silicon atoms are all, you know, happily hanging out in this perfect crystalline repetitive structure where each one of these is a silicon atom.
Well, they're a little bit dirty.
They're a little bit dirty. You want to add either some P or N type, depending on the flavor of the week.
The substrate is not doped.
The substrate can be doped, actually. The substrate is typically lightly doped.
Lightly.
Yeah, so
like salted.
Yeah, so this would be like a light P type.
Okay.
Light P. So maybe we added a little bit of boron, you know, to accept some electrons.
Spicy.
But what you put on top of the silicon, if you grow it, you can put this you can either grow this by putting it in an oven with oxygen, or actually doing what's called chemical vapor deposition. But you make a layer of silicon oxide. So silicon with a little bit of dopants, whether they're P-type or N-type. P-type are electron acceptors, and N-type are electron donors. This is the semiconductor part. And this is an insulator. So
O-type.
Yes. So the way you make a semiconductor, you start with your base wafer. It has a layer of silicon oxide. You can control how thick that oxide is based on what you want to make. And then you use you can use photolithography, or you can use direct electron beam printing, which is like laser printing for semiconductors.
You could even use crayons if you wanted to do something like centimeter level.
Yeah.
Grade.
Yeah. If you
The
wanted to
transistor's
make
this big, you could just draw on it with paint.
You could. If you wanted to hand draw a semiconductor and photo etch it in your basement, you could do that. And I think people have done it.
It would just be very big. Probably only Jerry's done it.
Jerry,
Ladies' night. You know, it would be great, really, one day if guys could learn this stuff.
it would be nice.
Okay. So.
But women, women can make semiconductors in their basements.
I know. This is just part of having uteruses. Okay.
Creators of the world. So what happens is you then put a layer of photoresist on, and you expose it. Your mask set is up here, and say I've got a hole, and I shine light in. Light comes through.
Except it's bent, so you have to take account for that.
Yeah, so that's hence these little angles. I either, depending on if it's positive or negative, I can either harden or soften the photoresist. And then I come in, you do processing steps to then etch away the silicon oxide where the photoresist isn't. And then you can take off the photoresist and then do it again and again. The other
You wash it off with something.
Yeah, it's things include hydrofluoric acid and other things you don't want to play with.
Yeah.
So HF is one of the more terrifying things
Yeah,
that
don't
are
try
used
this.
in
Don't try this at home
processes.
unless you're Jerry, basically.
So what happens is, let's assume this square part is gone now, is then you can actually, new drawing, update. So if you have silicon, let's say now we went through the photoresist step. This is our SiP, this is our oxide. Now we have an opening in the silicon oxide, and you can either surround the whole wafer with the next dopant you want to add for making, like if this is a P-type, maybe we want to add some N-type
So you
material.
diffuse in some N.
Yeah, you diffuse in some N, and literally it's diffusion.
And whatever this material is, it doesn't attach to silicon oxide.
Correct.
It just washes right off, but it does chemically
Diffuse in.
sink into and permanently.
Yeah,
It doesn't wash off.
Well, because it goes from high concentration to low concentration, and then you can treat it with pressure or humidity, or even do direct ion
fix it.
implantation.
Yeah.
Well, no, to force it into the structure.
Yeah.
So a way of thinking about it from the side is that
Do they ever do a sort of electroplating where basically you force it by creating, basically putting a voltage potential across it?
no, but you do that for metalization.
Okay.
In a way. So the way to think of it, another way to do doping. So like you can expose it to a concentration gradient, right? So where it goes from high concentration to low concentration.
And is it
forces
gas or
itself
is it
in.
liquid?
It's typically gas.
Okay.
Yeah, it's all in a gas processing machine. Or you can. So this is just gas diffusion. Or you can do ion implantation.
That sounds painful.
Well,
I think my dentist does that.
it's really high energy, right? So you have a little ion gun,
Oh, this is so violent.
and you shoot ions in, right? And because you control the strength of the beam, you can control how far it goes into the semiconductor.
This sounds more expensive than the gas process.
It can be, but it's really based on what you're trying to get in and how deep you need the diffusion to be, right? Because if it's
Because you want the
equivalent,
channel to be larger to carry more current?
yeah, cross-sectional area, that's definitely part of it. Or yeah, you need more power in the device. You need a larger junction. So there's a lot of different stuff. And this is not perfectly uniform. Like this area of doping will be really high, and then this area of doping will be a little
Yeah, it's not like
lighter.
on,
It's
off.
not
It's-
perfect.
It's diffusing in.
Yeah.
Okay.
And so, but this is what semiconductor process controls are all about, is making sure you can do this repeatedly.
Okay, but in
The
very,
device
very
comes out well.
small.
Very, very small.
Very, very small, and then you do multiple layers, and you can add more layers, and you plate. Basically, you can. It's like an oil painting. You just add more layers, and you scrape some off, and you add some on, and you.
Right, but you don't generally remove the base layer of silicon. So you're messing.
No, sorry. You do this basically where you photolith,
Right, and it's additive.
and
yeah.
then additive,
and then you take the photolith off.
Yeah.
And then you can do it again and add new patterns if you want to add different dopants.
Sorry, is the photo? Would you ever add a layer of some other material, photolith, and then etch away, or is it?
Yes.
So you do? Is it an etching process or is it an additive process?
It's typically so you do doping by doing the photolith. You add the photolith and you etch that away,
Yeah.
so that you can get access to the material underneath only where you want it.
Yeah.
And then you wash the photolithography off and you do it again.
Yeah.
To put stuff in different areas, right? So if I wanted to put
But are all wafers? I mean, the most basic wafer is going to be like And what we studied was like, here is how you make an NPN transistor, or like here's how you make a diode, or MOS or whatever. They had like one layer of silicon. Do you ever have like multi-layer? You do metallization multi-layer, right?
You do metallization multi-layer, but you typically, all of the stuff I worked on, you only had one layer of silicon.
There's no three-dimensional silicon. Like you basically have your...
No, because what happens is when you even take your silicon wafer and say this is like where your silicon starts, the first time you expose it to oxygen to grow the silicon oxide, the oxide grows down into the silicon and up from the top. And you don't get more pure crystalline, if this is all your SiO2. So you don't get any more pure silicon than what you start with.
Okay, yeah.
You can add dopants.
But just metallization layers.
Yeah, and the way to think of dopants, it's like silk screening, right?
How do
like
they isolate the metallization layers?
So you, so metallization can be put on with, I believe you can do some etching of metal, like you can put on a whole layer and then etch it to relieve it. I don't know that works very well. So this is where I get a little fuzzy on the details of the process engineering.
That's okay. You're just here to entertain me.
But you can do, have you ever seen sputter coating in patterns?
Yeah, I have seen it for like metallics, yeah.
Yeah, so you can put down another mask and you can sputter coat through the mask to add metal in layers.
Yeah. It's just three-dimensional. This is like three-dimensional fun.
Yeah, so it's, so the way I like to think of it is that the different diffusions, so adding different dopants of different levels, right? Like either really highly doped, lightly doped, is really akin to silk screening. You have a 4-color process, you have 4 screens. So you have 4 separate masks for doing, P and heavy P plus, N plus.
And then
or different types of P and N based on what you want in your process, because there are many different dopants.
I know there's because there's usually like transistor logic processes, and there's like FET, MOSFET,
right, and
JFET, and then there's like you can't really mix them, and you kind of have to or you can, but you have to kind of be.
Right, and they all require different dopants. So you can't actually accomplish everything on one type of IC, which is why in some packages you actually have what's called an MCM or a multi-chip module, because one part of the module.
Sensors are,
all of these systems on a chip, they're not a system. They're not an 18 millimeter square die. They're actually smaller dies that it's easier to make with better process controls.
They bond them inside.
Bonded inside. Yes.
Which is kind of like obvious, and like nowadays, like I get chip sensors. Like I don't have any here, but I have sensors that you look on it and it's a chip. I mean, it's a PCB.
Yeah. And
they actually have, it's like, it's 5 by 4 millimeters, but it's actually a small PCB, and they clearly have bonded like 2 or 3 chips inside, and then, it's because it's like
they put it in epoxy.
There's an accelerometer and there's a magnetometer, and they just bond it, and it's like, this is crazy, but whatever.
So you're seeing inside the IC package exactly what you see on the wafer itself, which is modules.
I've seen x-rays of I know that the chip that we use for cellular, like the MT6260, is multiple processors. Yeah. And like front ends and stuff inside. Yeah. Okay, so but I want to look at these like beautiful wafers again.
They're really stunning.
So let's look at these wafers again. So so we got this memory bank. So question is, why is there 2 banks? I wonder why that is. Maybe just the way dividing the memory by odd and even.
No.
It's kind of
that wouldn't make sense. I mean, so you took processor architecture too.
I know. Look, and I 6004. I totally did it, but I built a computer, but that was a
long time ago.
I'm kind of old.
Yeah, we forget these things.
I'm old. Okay, and also we did it. You don't physically build it. It's all in software. So it's interesting. It looks like there's 8. I can't quite count.
So they're like memory banks.
So
that's
it looks
8.
like 16. So maybe this is 32 bits wide. Maybe this is 2 memory banks that have different. I mean, it's not unusual to have 2 memory banks, but I think they're both flash.
Do you typically use them for parity?
No, I mean maybe one. One bank would be for high memory and one for low memory or something.
Probably, and each one has. So I worked a little bit when I was at Intel. I actually worked on flash memory, and I worked on the part of the memory I worked on was the error correction codes, or error correction scheme for the interface. So this is actually the memory driver.
Yeah.
Right.
And there's on the bottom and on the top as well.
Are there registers?
No, I think registers are not...
One of these rows would be a register,
yeah,
to be honest.
It's going to be... The thing is, we actually don't know how physically registers are implemented, but they wouldn't. I think this is flash memory, not RAM. Although the things I don't know. Like there has to be some flash, and there's also this like reddish thing here.
That could very well be a non-die capacitor.
Okay.
Right?
Yeah.
You need a lot of area.
No, because they're huge.
They're huge.
Like, yeah, when we did MOS caps, they're like, hey, it's like you do the math, they're like it's 3 picofarads. So if you want any
real like power, yeah, this might actually be the capacitor to handle all the switching current from the memory.
Yeah. Another thing is that you need. I mean, for memory, don't you need like a higher voltage, and so you sometimes have a switch cap? I mean, can you remember?
Or you mean like an on-chip boost? Yeah. So flash actually takes a higher voltage to write than it does to read.
To erase.
To erase.
Because it used to be you'd plug in 12 volts, and then I remember vaguely reading like, oh yeah, it's done on chip now. Although I don't know, that it could also be a filter.
Yeah. So I mean, these can be components for a power converter. But this is definitely the memory interface, because what I worked on at Intel was they basically said, we have a flash memory of this size. It has this type of internal addressing structure. We want an error correction code implemented in hardware. You have this much area, which translates to this many gates. Go.
Yeah.
And it was, I mean, I was just a co-op, so I did this design. I have no idea if it actually ever went into the IC, but it's what my manager's career was built on doing on-die ECC systems, right? And now like ECC, CRC, all of this, built-in checksum on memory where the processor gives you a fault if the memory is bad.
Yeah.
That's all built in now, but I was working on that at Intel in the early 2000s as a co-op, which was really cool.
I wonder how you do it. I mean, is this flash or RAM?
I can't tell.
But no, I'm thinking
out loud.
I know that we know because I've asked like 3 times, like, what is this? But I'm wondering, eventually I should look up how you know. I like these X's over here because I wonder what those are. And then
so typically, even if you don't have anything to put there, you have to put dummy diffusions. You have to put dummy metal, because if think of the wafer like a piece of tissue that you're delicately putting things on, and it really is.
Yeah.
If you don't have an even distribution of diffusions of metal and of oxide, it'll warp. And if it warps in the process, since it's photolithography to make it, you'll have failed yield, you'll have internal stresses.
Sometimes PCBs do that too, right? They have like, oh, you can't have uneven copper because of the etching process.
And so they do thieving to add copper where there wasn't any before because of uneven plating. It's the exact same for semiconductor wet etch.
Yeah.
So those actually just might be placeholder metal.
These might be, I mean, registers, I'm wondering, registers are SRAM, but they would be connected to the latches that would actually turn on and off sections. So I wonder if like registers would actually be like over here. I don't know. Yeah, this is like a kind of a mystery. Yeah. This is my first wafer. But
you're right. You're right that this is actually the large block is probably something like RAM.
Oh yeah, it's definitely memory, but it's like whether it's RAM or flash, I don't know. I mean, the thing is that there's actually not a lot. Most processors don't have flash, so it's probably RAM.
Okay.
Right, because like most.
Yeah. No, they don't. They actually usually
have the external flash chip. Well, we don't know what this is.
And flash is newer, and it really depends on when these were made.
That's another thing. It's like these look fairly large. Maybe they're older. Maybe this is pre-flash.
The fact that we can see the grid structure indicates to me that this is an older process.
Yeah, no, it's a little bit. Okay,
like, so I think a lot of, you know what, now that I think about it, a lot of our stuff at Analog was 300 nanometer.
Okay, so now this is much more like, I don't want to say reasonable, but like, okay, compare this, which is out of focus because whatever, but this huge ass chip, and to this chip, which is much more modern looking, right, much smaller.
So this has little small sections of memory in it, from what I can tell, right?
Hold on, this is, yeah.
So you see.
Hold on, I got it. People are gonna freak if I don't totally zoom in perfectly. Don't freak. Okay.
Oh, so you can see the buses. Do you see the bus?
Oh yeah, that's so cute.
The bits on the bus go up and down, up and down.
High and low,
high and low,
high and low. Okay.
Yeah. So
that's a little memory bus.
This is a bus, right?
That's so cool.
And so there's another bus here. And so let's move this down.
This is the information superhighway.
It really is.
Okay, so now you can see this. This has multiple different memory chunks. I think these are clearly different. And what's interesting is they definitely all have this you know, maybe there is like a parity thing. Maybe they actually, all the memories doubled and they do 2 banks. I mean, I don't think so, but like, it's interesting that all memory is doubled.
Yeah, yeah. This is redundant, that's redundant. Everything is redundant inside here. So each one of
Maybe, yeah.
these is actually the pad.
That's the bonding pad.
And it's not just the bonding pad. It's actually things like when you look at the IC diagram and they show you ESD diodes or
there.
input pin capacitance,
Yeah.
all of that goes in the pad design. Because you want to deal with anything nasty from the outside world before it can get into the die, because once it gets into the die, you're toast. This is just like you put ESD and protection diodes and resistors on all of the connectors on your PCB.
Yeah.
You do the exact same thing on an integrated circuit.
Yeah, so maybe like this part over here is flash, and then that's RAM, and then down there is registers, because that's, I mean,
yeah.
because if this is where the logic, I mean, that's logic.
Yes.
So that would be where like maybe,
Yeah. So,
yeah. Neat. I like that buzz. That's cool. Like you
so-
totally spotted that.
So let's pretend that like you've got some multiplexer cloud. Oh, you know what? The other thing that these can be, these areas here,
Yeah.
is particularly when it's much more uniform like that, is it can be the digital logic block.
Really?
Yeah. So if we can go to the big cam, or do a parallel
The hover.
hover cam.
Yeah.
So because I was talking before about metalization, right? So say
Yeah.
this is my die, and say this is my wafer. And I'm going to ignore the diffusions, and I'm just going to say that I've got Met1, and then I've got Met2, and I've got something bridging them, right? So I've connected wires with Met1 and Met2, that these wires are bonded to the semiconductor in different locations. Now, if you're doing...
So to trace, basically.
Right. So if you're doing straight up CMOS, just nothing but, TTL logic. Let's forget...
I'm a CMOS kind of lady.
Well, I guess TTL is current mode. But yeah, if you're doing nothing but CMOS, the easiest way to make that is to have a sea of gates. And a sea of gates. So you're...
This is actually, that's the name of the Radiohead album coming out tomorrow.
Wow, that's awesome. So if you have a sea of gates, right, and your typical step and repeat gate structure is
You got your
CMOS, right?
All you have is just latches and flip flops and
Or even even without that,
inverters.
if all you had was like CMOS inverters, and you had to build a whole digital logic structure out of that, you can do that by connecting them in metal. And so what you do is in your diffusion process, you do all the diffusions for sieve gates.
Yeah.
And then if you get your logic a little wrong, so like what you can do is you can put your wafer through, you might want to go to the other pretty wafer cam here.
I think Phil. We're running out of
Wafer
film a
cam.
little bit.
Wafer cam.
Okay.
Wafer cam.
So you
So-
have like a gigantic ocean of all these gates, and then you just can just decide
How to connect them in metal. So we actually
It's
had...
like a CPLD-ish.
Yeah, well, CPLD does it with the programming logic.
Yeah.
But the way to think of it is that if you have an oh my god, we got the logic wrong, and by the way, on one of our chips, we got the logic wrong.
That would never happen.
Someone rotated the address matrix for our parallel interface bus by 90 degrees.
Okay, well that's cool.
And so what happened there was you could, if it's a sea of gates implementation, you can fix it at metal. So if you have a bunch of you put the wafers through in a pipeline, right? Just like with the PCB, first you do, the PCB itself, but then you do the assembly. Having things held post-diffusion but pre-metalization means that if you find a mistake in the metal layer, if you find a mistake that you can fix by changing metal, then that is way cheaper than starting the wafers over from scratch.
Yeah.
And so then you just cut new masks for metal, and then you start running them through the process again.
Okay. What should we do? Okay, so we should get near the end of our thing because we're running out of fill. But do you want to like just look at some other ones?
Yeah.
Okay, so let's look at this one. So this one's just really.
There you go.
You can sort of
Perfect.
see it on this one. That one's even smaller.
Yep.
I don't know what this is. Yeah, we need to get a high-powered microscope here is what we have to do.
You also, I think, need a layout engineer. They can tell you what all the different structures
That's
look
no
like.
fun. Okay, so this one, well, we actually kind of looked at the most interesting ones. We looked at this. Did you
That
look at
one
this
is
big chip?
really bizarre. We
This
did
one
not
is-
look at the big chip.
This one's huge. Okay, we actually have to back this up because it's so big. Oh my God, Becky, look at this die.
It
It's
is
just
so big.
Big.
What do you think is the average size for a die?
I mean, I'm assuming that this is actually kind of hard to
Hard to
get
light.
images of because it's just so
So big.
gigantic. Yeah, I don't even know what this is.
This is huge. This has got to be a really old process because I think each dot is an individual gate.
Yeah?
Yeah.
Cool. Hi. There's one gate. You can like actually wave to them.
Yeah,
it's
you
not
can
so
see
bad.
you can see the diffusion patterns. I would say that this is a really, really large process.
This is so cool. It's like this little city. Hi.
Yep, very cyber.
I mean, this die is like, it's like a centimeter on the side.
Yeah, so the largest chip I ever worked on was 18 millimeters square,
Yeah.
or 18 millimeters on the side, and that was insanely large. It's like the Titanic of integrated circuits. That was not an analog. That was IBM.
Okay, and then there's one last one.
But there's the human, there's the hair.
No, that's me, because I...
But you can see it's on the order of this is clearly
Yes.
like a wicked old school process because this is the feature size.
Okay, I thought you were like, that has to do with the chip. I'm like, no, that's just me
No. But
shedding.
it's for comparison,
Yeah, that's a good comparison.
right?
Okay, and then there's this one, which
This
is...
and this is a much newer process. It's much denser, right?
Yeah,
You
I
can't
mean,
even see like
we can't even really
if
make out what's going on.
if each one of these little pads is your digital logic area, you can't even see the gates. Right?
Yeah.
It either
Yeah, who knows what's going on?
Who knows what's going on
I mean,
there?
there is something going on, but... like,
I really bet that so look at how tiny the pads are compared to the previous IC we looked at. So
Yeah.
these are the bonding pads. This is digital fabric right here.
yeah, you can't see what's going on. Okay.
Yeah, so the analog blocks are always larger and like
Yeah.
look weird but repeat. And then
Yeah.
the digital blocks are these sea of gates.
That's
grids.
why maybe when I looked at gates, it looked like, you know, that the chip that we saw, this one, where you saw the bus, that's what I imagine chips look. I don't usually think of like bricks that
Yeah.
are used.
Yeah.
Okay. I think we're done with this tour. How you doing, Mr. Lady Ada?
Oh, fine.
Okay. The cat is. Do you want us to grab the cat and make him
I'm
appear?
gonna bring the cat over to you.
Okay.
Okay.
Well, that was like an amazing tour de silicon.
Actually, the cat's gonna.
Hey.
You're welcome. Hey,
Hey.
MOSFET.
Hey.
Speaking of,
Aha.
it's your namesake.
This is the
This is where you
diffusion.
came. This is where you came from.
This is a diffusion layer, and then we coat him with peanut butter. No. Moss.
You have to diffuse love into MOSFET
Yes.
from high
Hi.
concentration into low concentration in his black heart.
Yeah.
Yes.
Okay. Well, thanks for coming by, and I'm glad. You know what? I didn't on purpose get this look. I mean, we could say I did, but I'm just glad that you came by and were able to shed so much light on this thing, because it's like
Yeah.
people see these, but like, what's going on here?
And it's really cool because, you know, working in medical for the last 7 years, I haven't gotten to think about semiconductors, and it's nice
Cat
to.
wants to hang out with you.
It's nice to. I think what happens as you get older in engineering is everyone refers to their previous life. So, hi, in a previous life, I,
Yeah.
did power engineering, or hi, in a previous life, I did this other thing, and so hi, in a previous life, I did semiconductors,
Yeah.
and it was a lot of fun.
Cat cam. All right. Well, thanks.
So thank you.
Thanks for coming by. Here we can
Thanks.
poke the cat.
Thanks for
with our feet.
having me.
All right. Later.
Two is better than one.
Okay. And that was that's so cute. Yeah, he likes you the most.
That's because I pet him.
Yeah.
It's because I'm warm.
Yeah, basically because you're warm.
Also, I'm new.
All right, well, that's a Adesco Lady Ada. Hopefully you learned as much as I did about semiconductor physics. My guest was, of course, Amanda the Wozniak, no relation, much cooler than the other Woz. You are.
Okay.
You are, just trust me. He's not on the show. He's not invited.
I've met both. I know
Yeah.
which one I hang out.
Yeah, we hang out with you. Thanks for watching. We'll probably do maybe a small video tomorrow. Maybe I'll do one about radio stuff. We'll see what's the news. Thanks again.
Thanks for having me.
Yeah.
Always a pleasure.
This was the Adesco Lady Ada.
All right.
Ladies' night.